Hello, let's start everyone.
Good time.
It's recording also. Hello. Okay. This is my lecture summary, and for technical reason, I don't have the lecture summary sheet, so I ask each team to make up your own. Just pick up a piece of paper and write your name, date, name, and then the lecture summary later. And this is a quotation that I was thinking last time when I talked about Gibbs phenomenon and thermodynamics. And this is a quotation that is attributed to the physicist Sommerfeld. Okay, thermodynamics is a funny subject. The first time you go through it, you don't understand it at all. The second time you go through it, you think you understand it. Except for one or two small points. The third time you go through it, you know you don't understand it, but by that time you are so used to it, it doesn't bother you anymore. That's thermodynamics at the high-flying level. Of course, many textbooks try to make it more accessible to undergraduates, particularly those who are more interested in working in industry. Okay, so that's, and I have posted report 5 problems. Okay, so, and note that I talked to KZ just before class, and that reminds me of the following. You notice that I have cut down a lot in in the report. This is the report from Team 6. Okay, in which you notice that I only asked you to, let's see, this is the projection on Fourier basis, and for n equal to 4. But you want to look at the report from last semester, and the reason that I asked to do 2, 4, and 6, so that you can observe convergence, and that's very important. Okay, so it's not just a matter of doing once and then leave it. No, you want to observe convergence because you don't know ahead how many, what's the value of n that is needed to have an accurate result. Okay, so it's a gradual process. And I'd like to come back to this report later. In particular, the graph matrix. Okay, all of you did this. You have seen, you have done this problem. You have seen the solution guide, and so think about this. And I have mentioned several times in my lectures. We'll come back to that graph matrix of the Fourier basis function. And today my goal is I want to continue with the street fighting Fourier series. Okay, discuss various properties of Fourier series. Right, so you saw a square wave, and then we'll do the sawtooth wave, half wave rectifier, and depends on time. Okay, so I'd like to start immediately with the continuation of the square wave. In particular, it's a misprint here. In particular, I have discovered a way to generate an infinite square wave, meaning going from minus infinity to plus infinity. You remember that at first I didn't know how to do that, and that's why in the animation 1, which is the link let me note down here, which is the link, the animation that I showed you in the last lecture. And let me zoom out and turn off the sine function here and use the projector mode and zoom out. You see that the square wave is not really going from minus infinity to plus infinity, right? It's just because I cannot plot that too many lines. So I just limit myself to 1, 2, 3 periods, okay? But later on, I found a way to generate a square wave that is going from minus infinity to plus infinity. So let me turn off a few curves so that I can show that to you. Here it is. Okay, so you see, if I zoom out, you still see the square wave extending, zooming out, still extending from the left to the right, zooming out, still, and so on, right? So it's really going from minus infinity to plus infinity. And the method is to use something called the sine function, sine, S-I-G-N, not S-I-N-E. Okay, so there are two words here that we use. One is the sine function that everyone knows, and the other is the sine, okay, plus or minus times. Okay, so how did I do that? So here, first, let me turn off the result and let me just show to you the sine function, right? So yeah, let me zoom in. Okay, so this is the sine function. I can also set s to 0 so that everyone is right here. Everyone is very familiar with this shape. And let me also let the amplitude to 1. Okay, yeah. So now this is a very, very familiar curve. But of course, I did something so that you see that the period really goes from minus 1 to plus 1. So I'll talk about that later. Okay, but just observe this. This is a sine function, and now you apply the sine function. Okay, so first I plot this. After that, I apply the sine function on the sine function, right? So what it does is that when the curve is positive, when the value is positive, then the sine function will give you plus 1. And when the curve is negative, it will give you minus 1. Okay, so let's look at the effect. If I click over here, you see that the green line is the square wave, and that goes from minus infinity to plus infinity because the sine wave goes from minus infinity to plus infinity. Okay, so this way I don't have to plot, each segment by segment. It's impossible to really plot from minus infinity to plus infinity. Okay, so that's one thing that is new compared to animation 1. Another thing that I did not mention last time, after I went back, I realized that I may have gone a little fast. So I'd like to go back to section 9b here. And on the window on the right, I would go down. You have seen this, we have discussed all of this, but there's only one point that I'd like to really connect you, and that is how I came up with this compact summation formula that allow me to do the summation, the animation. So let me use a middle window so that I can zoom in. First I zoom out so you see where I'm navigating. And so right here, right? And I zoom in back. And I just want to explain to you. So in the pedestrian, and put on the mask. Right? In the pedestrian method, you get the Fourier series, but there are too many terms. Right? And another thing that you notice is that, okay, this is a sine series, but not all of the b coefficients are non-zero. There are certain b coefficients that are zero when the index, the subscript, is even, and so the coefficient would be non-zero with odd indices, right? So and so therefore this is the Fourier series here. Now to convert this into compact summation form, you see this factor here, 2i plus 1, with I being the summation index, right? Now 4k over pi is the same. There's no issue there. So in order to express the sum of all of these sine terms into a single compact summation, you see what you notice is that all of these factor or number would be odd number, right? 1, 3, 5, and so on and so forth. And in the argument for the sine function, you also have 1, 3, 5. So I convert the odd number into 2i plus 1, because when I goes from 0, 1, 2, 3, if you multiply by 2 and plus 1, you get an odd number, right? So if you write a table, you would see better. So let me clear out. Maybe, yeah, if I write over here I, and then 2i plus 1, and form a table, then everyone would see for I equal to 0, 2i plus 1 is 1. For I equal 1, 2i plus 1 is 3, and so on and so forth, right? For I equal 2, 5. Okay, so that's how you basically summarize the series into a compact summation form. In problem 5, there's a problem similar to that, but I probably may not ask you to do that, you know, just to shorten the report. But on the other hand, remember, you are asked to work on all problems, okay? But you don't need to write the report for certain problems or only for selected problems, okay? So please, just for the sake of education and maybe prepare for the exam, do all questions, all problems as stated. Okay. All right. So and so with that, I'd like to continue on with the animation 2. So what is new here? What is new in the animation 2 compared to animation 1? Okay, so so animation 2 is right here. Let me bring up animation 2. Now you have seen that with the animation 1, you see that I can change the period, right? And let me see here. And if I increase the number of terms, okay. And let me turn off the sine curve right here. Turn it off. So, and this is you have seen before, okay? Let's say, for example, this is Fourier series here with when gap m is equal to 12, so essentially 13 terms, right? 0 plus when m equal to 0 is 1 term. And so you have seen the effect of changing the period and changing the amplitude that I showed before. Okay, so this is changing the size of the period and changing the amplitude is right here. This is the slider for the amplitude. The Fourier series follow, okay? But what is new is this. What if you are given a function? Let me turn off the Fourier series here. What if you are given a function that is completely arbitrarily placed, okay? Meaning that the origin is not at a point such that the function is odd in a period, it's completely arbitrary. You know, this is, and not just that, you also can have the square wave placed arbitrarily in the vertical y direction. So that is, for example, here. Oh, let me see. Wait. That is a coefficient that I have, or maybe in another animation.
Was it S coordinate shift?
Well, S. Okay, I'll explain S. Okay, and I'll explain to you. Yeah. So in this animation, I have only translation along the x-axis. Okay. So if you are given a problem where the square wave is completely arbitrarily placed like this, okay. So what is the street fighting method to expand this function into Fourier series in the most efficient way, in the simplest way? Okay, and that is really in section 9A with a lot of math there. But the street fighting method, maybe I let the class contribute while I look up my list of active learning credit. Think about it and contribute. You know, you can discuss with your teammates as well. Let's see. Here. Anyone? What's the easiest method to expand in Fourier series something that is completely arbitrary like this one? Casey?
Maybe changing the coordinate.
Shifting the coordinates, yeah, change the coordinates so that the origin is at this point, right? That would basically bring back to what you had before. So essentially, if I shift back to 0, let's see, when s is equal to 0 here, and this you know how to do the Fourier series for this part. Okay, that's what we did in the last lecture. And once you obtain the result, you would shift back to the original coordinates, okay? And that is written here. You know, so you basically change. It's like in the new coordinates, you have x tilde, and the old coordinates is x minus s, okay? This is new, and this is old. Okay. So in the x tilde coordinate, things look simple. This is the x tilde coordinate here. Then you expand into Fourier series in the new x tilde coordinate. So you note down here. So from here is x tilde. Okay. And then after you obtain the Fourier series in the x tilde coordinates, you replace x tilde by x minus s. And that's how you would obtain the Fourier series in the old x coordinates. Okay, so let me demonstrate by doing the following. Let me remove, clear the ink, and turn on the Fourier series. Right, so this is the Fourier series in the x tilde coordinates. Now you see that if I move if I translate the square wave along the x-axis, the Fourier series move with the square wave. So that means that the Fourier series is correct for any arbitrarily placed square wave along the x-axis. Okay? Yes, Kevin.
Do you have to like take into account the movement with some sort of transition, like?
Yeah. So the question was, did I account for the translation
for non-odd function? Yeah. Do you have to make it odd again? Is that what?
Sorry, I didn't understand. You know, this is already accounted for the translation. Right? because you see that the Fourier series follows the square wave. Wherever I move it, the Fourier series, the black curve, moves with the green curve. So indicating that regardless of how much you want to translate, the Fourier series would move. Jackie, do you have a question? No? Okay. So let me note down KZ and Kevin. KZ is team 2. And Kevin, you are what team number? Team 1. Okay. All right. Let me show you where in section 9A this was done. Okay. So let me look up section 9A or section 9 right here and zoom out and just go down so you see it's right here. Okay. There are two ways that you can change the coordinates. First, given a periodic function, and the period is arbitrarily from A to B, you know. So you see that this origin here of the old x coordinate is not in the middle nor at the left end. So there are two ways that you can do so that you can simplify the computation of the Fourier series. One is to move the origin to the middle, right? And the new coordinate is x bar, or you can move the origin to the left end and call it x tilde. Either way, you can have simpler way to compute the Fourier series because you can take advantage of odd or even function. Okay, so when I move to the middle, I call x bar. So probably in the previous example, I should have called x bar instead of x tilde, because x tilde is reserved when I move the origin to the left end, right, of the period. Okay, but that's basically all of these mathematics in this section. Basically, just describe what I did in the street fighting method earlier. Okay, so let's go back to the animation. And oh yeah, so you see when I translate like that, you see that I can also change the period, right? The length of the period, and I can also change the amplitude. So not only that my square wave can be arbitrarily placed anywhere in the x-axis, but it also accepts different period and different amplitude, right? Now I can even do better than that. What if you say, well, what if my square wave is completely arbitrarily placed in space, right? So here it's still, you can still see that it's still symmetric about the x-axis, right? But what if it's completely, you know, anywhere in space, not necessarily symmetric about the x-axis? And that I have in the animation 3, which is even more general than animation 2. And let me turn off animation 1. Okay, so now in this animation 2 here, let me turn off the Fourier series, and to show to you that I can place the square wave anywhere arbitrarily in space. You see that I can move it along the x-axis, and there's a slider I call K. I can move it anywhere along the y-axis, right? So you see that the square wave is completely arbitrarily placed in space. Okay. So what is, if you are given a function like this, what is the street fighting method to find the Fourier series for this? So we have Brandon, we have Kevin. Anyone else? Let's start with Brandon.
You have to do undivided k to subtract k from the function, then it'll reset it back to where it does.
Yeah, so basically you move both x and y, right? You shift the coordinates both along the x-axis and along the y-axis, so that you can bring the origin let's say this is the origin. Let's say this is the original curve that you are given. Okay. Then you want to move this origin to, let's say, this point here, right? Because if you work with this new coordinate system, let's call it x bar or x tilde, it doesn't matter what, x bar, y bar. Then in the new coordinate system, and the old coordinate system is right here, this is x and this is y. Okay. So in the new coordinate system, you know how to expand into Fourier series, because you know it's an odd function over one period, and that's what we did with animation 1 in the last lecture. Okay. So once you obtain the Fourier series in the new coordinates, you just shift it back. That's basically what I did right here. Okay, so you see that shifting in the x coordinate, so replacing x bar by x minus s, right? And then shifting in the y coordinates is with the constant k here. Okay, so that, now watch. Let me turn on the, so let me shift let me turn off here, and let's set k to 0, right? So that's a square wave that is centered about the x-axis, and let s equal to 0. So you see that, and let me zoom in, and this is now the origin is in such a way that the function is an odd function, like we did last time, and this is the new coordinate system. This is called x bar, and this is y bar. Okay, and you know how to expand into Fourier series, and so let's turn on the Fourier series with k equal to 0 and s equal to 0, and that's right here. And you see, and you can also change the number of terms, and you observe the same Gibbs phenomenon that we already talked about last time. You know that you do not have convergence at the point of discontinuity, regardless of how many. And here I have 51 terms in the series, right? Now, note that if I change k, you see the series move with the square wave. Okay, and if I change s, meaning shifting along the x-axis, it's also changed. So and this would be an example of an arbitrarily placed. Let me zoom out. Fourier series. Okay, and yeah. So now let's demonstrate that the Fourier series, you know, you do have convergence for an arbitrarily placed square wave. Okay. All right. So basically, that's the street fighting application of this section 9 here, with all the mathematics that you saw. Okay. It's basically just transformation of coordinates. Okay. So to obtain simple Fourier series before you transform back. Now this lesson is very important, and keep this in mind. For example, here, maybe I should bring 2 windows so that you can see. Okay, so suppose that you move the origin to the middle of the period, and the new coordinate is x bar, the old coordinate is x. Okay, then the formula for expanding into Fourier series is here. Okay, but keep in mind this is the x bar coordinates. Okay, in the new coordinates, the same Fourier series and the formulas. Note it's the integration from minus L to L, minus L to L, minus L to L, where L P is equal to 2L and L is defined like this. Okay. So in the new coordinate x bar, you integrate from minus L, minus cap L to plus cap L as written here. All right. And A bar 0 is over there. Okay, so very good. And the same thing for if you move the origin to the left end of the period, right here, and that's the x tilde coordinates, and when you integrate, that would be from 0 to 2L, right? And let me show you the formula. Let me clear the ink. Okay, clear the ink here. And if you move the origin to the left end of the period, so the new coordinate is x tilde, then the formula for Fourier series is very similar, and it's right here. Okay, this is the Fourier series, but note that the variable is x tilde, right? And the coefficient a tilde 0, a tilde n, b tilde n are computed with the integral using x tilde, and the integration limits would be from 0 to 2L. Now the factor over here remains the same, right? 1 over 2L for a tilde 0 and 1 over L for a tilde n and for b tilde n, meaning that for the average the factor has to be 1 over 2L, whereas for all the coefficients of cosine and sine, the factor is 1 over L. Or maybe you want to keep in mind that this 1 over 2L is actually 1 over P, right? Oh, I even wrote it down here already. Let me erase here and right here. You see, 1 over 2L is the same as 1 over P, but 1 over L is really 2 over P. Okay, it's really 2 over P. Same thing here. Keep this in mind. Keep this in mind, and keep in mind the problem that you did in report 4. Okay. Maybe that it's now a good time to take care of this. You know the Fourier series. Let me use the middle window to zoom in. Right here. You see, so here 1 over 2L is really 1 over P. P is period. Period is 2 times cap L, and 2 over P is the same as 1 over L. Yeah, here I also wrote that. Okay, so I already have it here. So 2 over P is the same as 1 over L. Okay. Now note that the Fourier series is an infinite series, right? And as I explained to you before, to expand a function on a basis, or to project a function on a basis of functions, is the same as projecting a vector on the basis of vectors, right? And the coefficient a0, an, bn are the components, just like the components of a vector that you need to find. Okay, so here's my question to you. In this example here, or in the case of function, you have infinitely many components because functions lives in an infinite dimensional space. It's something that maybe that is the first time you are encountering because you are used to vectors in 2D space, in 3D space, or 4D space, but you rarely deal with even 5-dimensional space or 100-dimensional space, right? Of course, you encounter that. You would encounter that in finite element method because when you model a space station or a car or an airplane, you would use hundreds or thousands or even million degrees of freedom. Right? That's an example of large dimensional space. But functions are infinite dimensional space. How can you find the components of a vector in an infinite dimensional space? Remember, what's the method to find the components of a vector in an oblique coordinates in general and orthogonal coordinates in particular? What tool do you need? What tool do you need? So let me bring up report 4 by team 6. It just happened that I looked at team 6, maybe there are other excellent reports. Okay, let me zoom in. Yeah. So can someone say something, particularly team 6? The method is written here. You just need to say something and get active learning credit. So we have Colton. Anyone else? Anyone else in the class? Okay, Colton.
You need the dot product.
Yeah, you need the scalar product. The dot product is for vectors. So you generalize the scalar product, and for functions would be the scalar product that is written like this, right? Casey?
I guess you would need the gram matrix.
The gram matrix, right? So the method is to form the gram matrix, and I'm not going back to that method because we have seen that many times already. So for functions, you also form the gram matrix, and that's what you did right here in this problem in report 4. Question once more. In the case where you have infinitely many coefficients, right? What would be the dimension of the gram matrix? What would be the dimension of the gram matrix? Remember, in this problem here, I asked you to limit to n equal to 4, right? So that's 4 basis functions. Okay, using the Fourier basis function, that is. And so this team here had a, so this is a 5, basically 5 by 5, right? Gram matrix. Now for a Fourier series, it has infinitely many terms, infinitely many coefficients. Correct? Plus 1 by plus 1. But remember, the upper bound of the series is infinity. So what would be the dimension of the gram matrix when you have infinitely many components?
Wouldn't it just be an infinite matrix?
The right, already Robert and Kevin, let's say, and also Paul. So Robert, sorry, did you say that also? Okay, very good. So everyone who said infinity by infinity, that's correct. That's very good. So Maria is team 8. Robert is team 5. Paul, do you agree?
Yes.
Okay. Very easy, right? So why not get the credit? And so direct is team 8. And yeah. But let me ask you this. Very good. So now everyone agrees that, you see, I hope that you see that asking questions is very important because it stimulates thinking. If it's just a one-way lecture, that put you to sleep. Okay. And Socrates, that's why the Socratic method is to teach by questioning, and I hope that students also learn by questioning. Let me ask you the next question. if you have a matrix that is infinite by infinite, how do you invert that matrix? Can MATLAB do the trick? Everyone has MATLAB, right? So we see that Anderson shake his head. Anyone else? Okay, so how do you invert this a gram matrix that is infinite by infinite for the Fourier basis function? How do you invert the matrix? Anyone? Can you invert the gram matrix for the Fourier basis function, Kevin?
Well, it would be like 1 over infinity, so it wouldn't go closer to 0.
Yeah, it's not possible to invert that because you said the determinant is like infinity and 1 over infinity. Very good. So are you stuck? So let me show you this. What I'm trying to drive at is to make a connection, right? So it's not enough just do something and then that's it. But can you connect? That's why you see. I think I did mention the quotation by Montesquieu. Right? Intelligence is the ability to see the difference between similar things and the similarity between different things. Okay. So how do you connect these formulas there with problem? What is it? 4.5, right? In report 4. In order to get this is the solution, right? Clearly, this is the solution. They already found the solution. All I'm asking you is, what is the thought process that would arrive at this solution? You need to invert the gram matrix, right? But if it's an infinite by infinite gram matrix, you know, in general, you cannot invert. Let me show you the gram matrix again, and I hope somebody can say something, because this is very, very important. Is it?
So you're saying, I mean, because we don't normally deal with infinity.
Right.
So what we're doing is truncating it.
Truncating.
A lot.
Well,
And
that's a
you
good
can-
idea.
You can
Truncate.
inverse anything that's been truncated.
Right. Yeah.
As long
So
as there's
if
a finite number.
yeah, even 1 million by 1 million in
Yeah.
principle, you can invert. Yeah,
So-
definitely. But this is mathematics. This is exact mathematics.
So, I mean, limits, take a limit
Limits,
to something,
okay.
limit to infinity.
Okay. Anyone else? Remember, this is involving. You know, they have the exact formula for you there. Anyone else? This is very, very important. Govan, you want to say something?
Could you, using truncation and superposition?
Truncation and superposition. That's the idea that Maria suggested. Yeah. Anyone else?
Is it a symmetric matrix that you're looking at?
Symmetric.
Is it?
Yeah, the gram matrix is symmetric. Yeah.
So what you need to do is the transpose.
Oh no. The inverse is not the transpose. The inverse of a matrix
This is one of.
is not a transpose. There is only one particular class of matrices which the inverse is a transpose. It's called orthogonal matrices. And that's different. That has nothing to do with. Yeah. But in general, the inverse is not the transpose. Okay, keep that in mind. That's very important. It is something much simpler than you think, Casey.
Well, in one of our methods, when we have an inverse, what we can maybe do is multiply by itself, or pre-multiply throughout by the inverse, and then multiply again by whatever our row matrix is, so they cancel out.
Okay, so here is very important. Brennan, you want to say something?
The limit of learning infinity is equal to 0. So you take the limit.
Limit, okay. Yeah, in a way, the idea of the limit is what Maria was saying, right? You truncate and then you take the limit. You know, it's simpler. This is exact mathematics, okay? You don't do like that, you know? This is a diagonal matrix. So you can invert a diagonal matrix simply by inverting each of its coefficients. That's all. That's as simple as that. Even this is, if this is infinity, right? Infinite by infinite. So the inversion of a diagonal matrix is simply by inverting its coefficient, okay? And you see, this is 1/2 here. That's why when you invert 1/2, you have the factor 2, right? So that's why, whereas the coefficient up here is 1, down here is 1/2 all the way through. So that's why in this formula here, You see now you see the reason. Okay, you learn two things. First, you learn how to obtain infinitely all of the coefficients in the infinite Fourier series exactly. Okay, and the inversion of the Gram matrix can be performed even though it's infinite by infinite because it's diagonal. It's a diagonal matrix. And the second thing you learn is why there's a factor 2 here. The factor 2 there is because the Gram matrix would be equal to 1/2 from the second element on. The first element is equal to 1, and that's why you have 1 for A0, but you have coefficient 2 for all the AN and BN. Okay?
And so that's applicable for any Gram matrix? Because we.
No,
Oh,
only,
no.
yeah, you see here, okay, last thing before
I'm
we
trying to
quit.
think back to the report.
This is only for Fourier basis functions, and the reason that the Gram matrix is diagonal is because of orthogonality. Okay, the Fourier basis functions are orthogonal to each other. That's why the off-diagonal coefficients are 0, because the scalar product of these basis functions are 0, just like for vectors. Right? Dot product of orthogonal vectors are 0. So please, lecture summary. And like I said, please pick up a piece of paper because I don't have the lecture summary sheet. So just use a blank sheet of paper, put down the date, your team number, your name, and your signature, okay? and the summary. Translation. No, first you fix the period, then you can translate it anyway. So translation is not affect the period. But the reason is because you are given a function arbitrarily placed in space. So all the trick is just move on to a convenient point so that you can see it. Once you have the new coordinates, you move back.
Well, I mean, until it's due at least. I'm going to start it this week, but I don't have anything over my head.
Get a negative sign, it's minus a point, but if you forget to multiply the mass, it's the same thing. On the negative sign, it'd be minus half. I'm happy now.
You're in it right now?
Yeah.